Welcome to Advanced Group Theory. Today, we are going to explore one of the most beautiful and foundational results in abstract algebra, known as the Jordan-Hölder Theorem. If you have ever wondered whether mathematical structures have a unique DNA or a fundamental set of building blocks, this theorem provides the answer. We will build our understanding from the ground up, so let us dive right in. To understand our main topic, let us start with a simple analogy. Imagine you have a complex toy made entirely of interlocking Lego bricks. You can take this toy apart by removing different chunks in various orders. However, when you finish, you will always have the exact same pile of indivisible Lego bricks on the floor. In group theory, we break down a group using a normal subgroup, which divides the main group evenly to create a quotient group. If a group cannot be divided any further, it is called a simple group. This is the mathematical equivalent of an indivisible atom. Now that we understand what simple groups are, we can state the Jordan-Hölder Theorem. A composition series is a step-by-step chain of normal subgroups, getting smaller until only the identity element remains. Every step produces an indivisible simple group. The theorem states that if a finite group has a composition series, any two such series must have the exact same length. Furthermore, the simple groups produced, known as composition factors, will be exactly the same in both series, even if they appear in a different order. This guarantees every finite group has a unique prime factorization. This concept leads us directly to the mathematical notation for a composition series. The formula shows a chain starting with our main group G, which contains a smaller subgroup G1, which contains G2, all the way down to the trivial group containing only the identity element E. For this chain to be valid, each subgroup must be a normal subgroup of the one before it. More importantly, the quotient group formed by dividing one step by the next must be a simple group. This means the mathematical gap between each step cannot be broken down any further. If you increase the size of the starting group, the chain simply gets longer, but the fundamental rule of indivisible gaps remains exactly the same. Before we prove the theorem, let us see this formula in action with a concrete example. We will find the composition series for the cyclic group of order 6, denoted as Z6. This group has elements 0 through 5. Since it is an abelian group, all its subgroups are normal. We want to build chains down to the identity element. For our first path, we divide by a subgroup of size 2, containing the elements 0 and 3. This subgroup is isomorphic to Z2. The first quotient has a size of 3, giving us the simple group Z3. The second quotient gives us Z2. Now that we have one path, let us look for a second, completely different path to break down the same group. This time, we start with a subgroup generated by the element 2, which contains 3 elements and is isomorphic to Z3. When we calculate the quotients for this secant series, the first step gives us a size of 2, which is Z2. The second step gives us a size of 3, which is Z3. Comparing both paths, the first gave us factors Z3 and Z2, while the second gave us Z2 and Z3. Both have a length of 2 steps and produce the exact same simple groups, perfectly verifying the theorem. Having seen a small example, let us verify the theorem for a slightly larger cyclic group, Z12, which has 12 elements. Our goal is to find 2 completely different composition series to prove that even with a longer chain, the building blocks remain identical. For our first path, we start with a maximal subgroup of order 6, generated by the element 2, and then a subgroup of order 4. Calculating the quotient step by step, the first division gives a size of 2, the second gives a size of 2, and the final step gives a size of 3. This yields the factors Z2, Z2, and Z3. Continuing with our Z12 example, let us construct a completely different path. This time, we will use a maximal subgroup generated by the element 3, which has 4 elements, followed by a subgroup generated by 6, which has 2 elements. we calculate the quotients in the exact same way. The first step divides 12 by 4, giving a size of 3, which is the factor Z3. The second step divides 4 by 2, giving Z2. The final step divides 2 by 1, giving another Z2. Let us bring both of these paths together to see the final result for Z12. The first path yielded the simple groups Z2, Z2 and Z3. The second path yielded Z3, Z2 and Z2. Notice that both paths have exactly 3 steps. More importantly, both paths produce the exact same collection of simple groups, just in a different order. This confirms that Z12 has a unique set of fundamental building blocks, regardless of how it is dismantled. The physical meaning here is that the structural DNA of the group is an absolute invariant. So we have successfully used the formula and seen it work in multiple examples. This brings us to the formal proof of the Jordan-Hölder theorem. We use mathematical induction on the size of the group. We assume the theorem is true for all groups smaller than our main group, G. To prove it for G, we assume the group can be broken down in 2 different ways, starting with 2 different maximal normal subgroups, which we will call H and K. Because H and K are maximal, the first quotient in each path is guaranteed to be a simple group. We assume by induction that the rest of the chains going down to the identity behave perfectly. Continuing with our derivation, we must address what happens if the subgroups H and K are different. If they were the same, the problem would be trivial. To solve the difficult case where they are different, we look at the intersection of these 2 subgroups, which we will call L. Because H and K are both normal in G, their intersection L is also a normal subgroup. We can use this intersection L to build a mathematical bridge between the 2 different paths. This step is crucial because it forces both independent composition series to share a common lower tail, allowing us to compare their building blocks directly. Now we apply a fundamental rule called the second isomorphism theorem to our bridge. This theorem tells us that the mathematical step from G down to H is identical in structure to the step from K down to L. Because of this perfect symmetry, the simple group produced by dividing G by H is identical to the group produced by dividing K by L. By routing both the H path and the K path through the intersection L, we prove that the factors on the left are exactly the same as the factors on the right, just swapped in order. This gives us our final result, proving the building blocks are identical. To make this proof completely clear, let us look at a visual representation of the bridge we just built. This is the diamond isomorphism lattice diagram. At the top, we have a main group G. The 2 paths branch downwards to the maximal subgroups H and K. They then converge at the bottom vertex, which is their intersection L. The edges of this diamond represent the quotient groups. The symmetry of the diamond perfectly illustrates the second isomorphism theorem. The top left edge is identical in structure to the bottom right edge, and the top right is identical to the bottom left. This visualizes exactly why the composition factors match. Now that we have proven the theorem, you might wonder why this matters in the real world. Think of chemistry, where knowing the atomic makeup of a molecule tells you exactly how it will react. In mathematics, knowing the composition factors of a group tells you its fundamental properties and symmetries. The Jordan-Hölder theorem guarantees that this atomic makeup is a permanent, unchanging property. This specific theorem actually launched the classification of finite simple groups, one of the largest collaborative mathematics projects in human history, aiming to list all the fundamental building blocks of finite symmetry in the universe. We have covered a lot of ground today, so let us summarize our key takeaways. First, the Jordan-Hölder theorem is the group theory equivalent of prime factorization, proving that every finite group has a unique set of simple quotient groups. Second, a composition series is the step-by-step chain that breaks a group down into these indivisible simple groups. Finally, we proved this using the second isomorphism theorem, showing that any two parts will always yield the exact same building blocks. You now understand the fundamental DNA of mathematical groups. Great job!